Okay, so here we have a submerged body example that I'm going to be working through, and yeah, let's get right into it. So part A asks us to draw a free body diagram showing all the vertical forces acting on the body. Now I've drawn a figure out here to the right to show this. So whenever we have a problem like this, we always need to include the weights of each one of these uh, different pieces of this body. Also, we'll have a force on the bottom that the tank exerts onto this body. And then we will have a buoyant force on one because it's submerged but it doesn't touch the bottom of the tank. And then finally we'll have a two-part force. So we have all this water up here. And we're going to have we'll call this FZ1, or we'll call this FZA, and then this one that acts through this triangle FZB. So, okay, that is part one completed. You have the three weights, and we have the force on the bottom of the tank. We have the buoyant force, and then we have the weight of the water force that acts on body 2 and 3. So that's part A completed. Now we have to figure out the force that the bottom of the tank exerts on the body. In order to do that, we have to sum all the forces in the z direction to 0, with positive being upwards. It doesn't matter if positive is upwards or downwards is positive, but just all these signs in this next part will be flipped. So just adding all these together, we'll have a negative weight 1, a negative weight 2, a negative weight 3, and then we will have a positive FB1, a negative FZA, and a negative FZB, and then finally a positive force on the bottom because that acts upwards. Now we just need to figure out what all these different forces right here are in order to find F bottom, which is what we're asked to find. So 0 is, this all added up is still going to be equal to 0 because this body isn't moving upwards or downwards. So first we have the weight of 1, which is simply the volume of 1 times the specific weight of 1, and in this problem we're given the specific gravity of each of these different pieces is equal to 2. So we first find the volume of 1, which is 2 times 3 times 6, just using the figure and the dimensions given in the figure. So that's right here, this is the volume of 1 times the specific weight of 1, which is 2 times gamma water. The specific gravity times gamma water gives you the specific weight of this particular body. Now we have the weight of 2, which is the volume of 2, which is going to be 4 times 2 times 6 divided by 2. That's the volume of 2, times the specific weight of 2, which is again 2 gamma water. We have weight of 3, which is going to be 5 times 4 times 6. 4 times 5 times 6. Then again times the specific weight of this body, which is 2 gamma water. Now we have plus FB1, which is the buoyancy force on 1, which is going to be the volume of 1, or the volume displaced, which is V with the line through it, times the specific weight of water. Now this volume displaced in this case is just going to be the volume of body 1. So we have the volume of 1, which is again 2 times 3 times 6 times gamma water. This isn't we're not multiplying this times 2 gamma water because this is simply the force that this is the buoyancy force, which is simply the volume displaced times gamma water. Then we have minus FZA, which is this force right here, this water, which acts downwards. So that's going to be 5.5. It's going to be the volume of that water times the specific weight of water, which is volume of that is 4 times 5.5 times 6, and then times gamma water, minus FZB, which is this portion right here, this triangular part right here, and that is going to be the volume of that piece, which is coincidentally the volume of 2, times the specific weight of water. So that's going to be 4 times 2 times 6 divided by 2, because it's a triangle, times gamma water, and that's FZB. And then finally we have the force on the bottom of the tank. And all of this right here, all of that is going to be equal to 0 when you add everything up. We know everything except for F bottom, which is what we're looking for, which is good. So now all we have to do is do a little bit of simple algebraic manipulation and come out with a value for F bottom, which will be 29,950 pounds. And that acts upwards. You have to remember units and direction on these. So that right there is the answer for part B, which just asked us to find the force on the bottom. Now this asks us to, or part C asks us to find the location M right here that F bottom acts away from A, which is right here. So we need to find this distance M for part C. Now to do this, we have to do a moment analysis about point A, which is that point right there, and use all these different forces and have them equal to 0, have the moments equal to 0. So we have the moments about A equals to 0, and we're going to say clockwise is going to be positive. Again, just like the summing of the forces, it doesn't matter if you choose counterclockwise to be positive, it's just all of these numbers that I'm about to write down will have opposite signs. So for starters, we'll just say F bottom times M, which is the moment arm. So this is going to create this right here is this force times the moment arm, which is what the moment the F bottom contributes about A. That's going to be positive because it's trying to rotate the body clockwise. Then we'll add the next one, which is going to actually be, we'll use W1 as our next one, which is going to be negative because this is trying to rotate the body counterclockwise about point A. And we use the force of, we use the weight of 1, which is 2 times 3 times 6 times 2 gamma water, times the moment arm, which in this case is this distance here to the centroid, which is right there. That's where the weight acts. So the centroid of that is 5.5 feet away from point A. So we have the weight of we have the weight of 1 times the moment arm of 1. Now we'll have the weight of 2, which again is going to be, the whole weight of 2 is going to be a negative value because it's trying to rotate counterclockwise. So the weight of 2 is 4 times 2 times 6 divided by 2 times 2 gamma water times the moment arm of 2, which acts at the centroid of this triangle, which is 2/3 away from this point right here. So that's 2/3 of 4, or 8/3. So we'll just say 8/3. And that's the moment arm of weight 2. Then we have the weight 3, which is the weight of 3 times the moment arm of 3, which is 4 times 5 times 6 times 2 gamma water times 2 in this case because it acts at the centroid of body 3, which is 2 feet away from point A. So those are our weight forces done. Then we are going to have our buoyant force, which coincidentally is almost the same as point 1, except it's going to be positive value. That should be a 3. So we have the buoyant force, which we found right here, which is 2 times 3 times 6 times gamma water times its moment arm, which is the same as the weight of 1 because that's where the buoyancy force acts at the centroid of the volume displaced, which in this case is just body 1. Now we get into the trickier part of things, which is FZA and FZB. The reason I split that up into two different forces is in order to do this moment analysis part, which you guys should probably get in the habit of doing. If we have some kind of composite shape like this with a triangle and a square or a rectangle, you should probably try and split it up. It'll make it easier on you guys. So now we have FZA, which is going to be 4 times 5.5 times 6 times gamma water, which we found right here. And that's just the weight of this water in this rectangle right here, times the moment arm of that, and it acts through the centroid of this of the volume above. So that is going to be 2 feet over, moment arm of 2. Then we have plus, and that's going to try to rotate counterclockwise, so that's negative again. Then we have FZB, which we found right here, which is 4 times 2 times 6 divided by 2 times gamma water times its moment arm, which is going to be 1/3 over from, which is going to be right here. Acts right about there, 1/3 from the base. So we have 4/3 instead of 8/3. So it's 1/3 instead of 2/3 of 4. And then that is it, I believe. Yeah, we have our 3 weights right here, right here, and right here. We have our buoyancy force, and then we have our 2 parts of our force of the water above. So now we have no unknowns except for M. We know what F bottom is. We know what all the gamma waters are. So if you solve this out, do some algebraic manipulation again, and we find out that the value for M is, I'm not quite sure what the value or what the actual number is, because the solution that is on Blackboard is incorrect. So you'll come out with some number once you do all these calculations, and that is your answer for M. So hopefully this helped. If you have any trouble with this problem, let me know, and yeah, hopefully this helped.